Hello, I'm Ravi Handa. Welcome to the session on real numbers. Any number that can be represented on the number line is a real number. For example, this 0, which divides the number line in two equal parts, the positive part and the negative part. 1, 2, 3, 4 and so on. The numbers that you can count are known as natural numbers. If we also include 0 in those, they are known as whole numbers. Considering the negative side as well, -3, -2, -1 and so on, they are known as integers. However, if a number can be expressed in the p by q format, where both p and q are integers, also q is non-zero, then they are known as rational numbers. Any number which is not a rational number is an irrational number. Let's look at a few examples. Are all natural numbers rational? Yes, they are, because any natural number that you consider can be written as that number divided by 1. 118, is it a natural number? Yes. Is it a rational number? Yes, because it can be written as 118 divided by 1. The irrational ones are of this format: root 2, root 3, root 5, something of the format of a root of a prime number. Pi is a very popular irrational number. As long as we are on classification of numbers, let us look at another classification, that is the prime and composite. Now, what are those prime and composite numbers? They are first of all come under the category of natural numbers. Prime numbers are those which are divisible by 1 and itself only. I think this only is the part where most students make a mistake. For example, 18 is divisible by 1, 18 is divisible by itself, that is 18. But then, is it prime? No, it is not. Why? Because it should be divisible by 1 and itself only. Any natural number which is not a prime is composite other than 1. Why so? Because 1 is divisible by 1, there is no itself or another case which comes into it. So it does not come under the category of prime numbers. It does not come under the category of composite numbers. It comes in a separate category for itself, that it is neither a prime number nor a composite number. Moving on with real numbers, let us look at Euclid division. The lemma says that a is b into the quotient plus r when a is being divided by b. R here is my remainder. Please note that the remainder has to be always greater than or equal to 0, but it will always be lesser than the divisor. The algorithm says, which is used to find out the HCF of two numbers c and d, provided c is greater than d. Then, using the lemma, I can express c as d into q plus a remainder. Once again, the remainder is greater than or equal to 0, but lesser than the smaller number. Now, if this particular remainder comes out as 0, then my HCF is the smaller number. However, if it does not come out as 0, then I need to apply the same process over and over again. Say, if it is non-zero, then I'll apply it on the smaller number d and r, which was the remainder. And I'll keep on continuing this process till the remainder actually becomes 0. I think we should take an example just to clarify things. Let's say I have to find out the remainder of the HCF of 240 and 1024. I take 1024, I express it as 240 into a certain number plus the remainder. Now what will I get? A rough calculation: 240 into 4, 960, 64 will be my remainder. My remainder is non-zero. As you can see here, I'll have to continue the process with the smaller number and the remainder. So I continue the process with 240, the smaller number, and the remainder 64. Now 240 can be written as 64 into 3, 192 plus 48. Again, a non-zero remainder. So continue. 64 is 48 into 1 plus 16. Again, a non-zero remainder. So I need to continue with the smaller number and the remainder 48 and 16. So I need to write 48 as 16 into something plus the remainder. But what do I realize? That 48 is indeed 16 into 3 and I get a remainder 0. And if I get a remainder as 0, whatever was my smaller number, which was 16 in this case, is the HCF. So the HCF, after this calculation, I can say for 240 and 1024 is 16. Now let's look at the Fundamental Theorem of Arithmetic. It's a very simple concept. All it says is that a composite number can be written as product of primes with their powers in a unique way. The order is not relevant. Let me take an example. Say for example, I am given the number 1176. Very clearly it is not a prime number. Let us try and factorize it first. It's divisible by 2, I think we get 588. Still divisible by 2, I get 29 for 294. Still divisible by 2, what do I get? 147. Now this is not divisible by 2, but I can look at it and say that it is divisible by 3. I get 49, which is nothing else but divisible by 7, and I get another 7. So the number that I have, 1176, can effectively be written as product of primes which are involved are 2, 3 and 7. Now how many times is 2 coming in this? 1, 2, 3. So the power of 2 will be 3. How many times is 3 there? Only once. And 7 is there twice. The theorem essentially states this fact, that the number 1176 can be written as product of primes in only one unique way. And this is that unique way. You can change the order if you like, but you cannot change the primes, you cannot change their powers. And this idea comes in handy when we are calculating the HCF and the LCM. What exactly is the HCF? HCF is nothing else but you look at the common primes in the numbers and take their lowest powers which are common. Very similarly, in LCM, you look at all the prime numbers which occur and then you consider their powers. Let's again take an example. Say I am given the numbers A and B, where A is 2 to the power 5, 3 to the power 4 and 7 square. On the other hand, B is 2 cubed, 3 to the power 5 and 5 squares. So what will be the highest common factor? Simply speaking, first of all, I need to look at what are the primes which are common. 2 is there in both of them, 3 is also there in both of them, and that is it. Now, I look at the highest power. Once again I repeat, the highest power which is there in both the numbers. That is 3, which is there in both the numbers. This is 5, this is 3. So the power of 2 will be 3. Looking at 3, what is the highest power there in both the numbers? It is 4. And so my HCF is 2 cubed into 3 to the power 4. Very similarly, looking at the LCM, first of all, I'll have to note down all the prime numbers which occur. They are 2, 3, 5 and 7. And then look at the highest possible power. What is the highest possible power? For 2, the highest possible power is 5 here. For 3, the highest possible power again is 5 in B. In the LCM, highest power of 5 is 2 and the highest power of 7 from here is 2. So these are my HCF and LCM. It also leads to one very, very essential property which can be used in exams, and that is HCF into LCM is equal to the product. Once again, HCF into LCM is equal to the product. But you need to remember that this is applicable only when you have two numbers. It is not applicable in all cases.